Right, let's do a recap. What's the difference between magnetic induction and induced magnetism? Right, got it? Did you get this? Magnetic induction refers to the material that becomes an induced magnet. So that magnetic material becomes a magnet when it is near or in contact with magnet, and in the process called magnetic induction. Whereas induced magnetism refers to the magnet or the magnetized object that causes another object to become magnetized through induced magnetism. Okay, so with this understanding of magnetic induction, we can now move to understanding our next part, which is how understanding how materials can become magnetized and demagnetized. Well, if you can recall from your early primary school days, we talked about various methods of making a magnet, such as stroking, as well as electrical method. Is this beginning to sound familiar? And we also talked about methods of demagnetization, such as hitting the magnet, heating it, and putting it in the alternating current. So in this portion, we're going to go a little bit deeper at the level of the magnetic domains to understand why this is so. Okay, so we're going to describe these methods and why they work. So let's start by going a bit deeper into explaining why things that you saw, such as stroking and using the electrical method, actually work. We need to have a theory of magnetism. First, let's look at the deeper into a north and south poles of a magnet. Now imagine if you cut this magnet into half, what do you get? Do you get a magnet that has north pole on one side and a magnet that has south pole on another? What do you think? Well, how about if you do a cut here? Do you have a magnet that has a north pole on one side and maybe south pole on another, and maybe in the center is maybe a mixture of both? Or none at all? So what do you get? Well, of course, the correct answer is actually, if you do cut them, you actually end up with three magnets, each with its own pair of north and south poles. Well, if that is so, then it must be obvious then that the north and south poles aren't really localized. In other words, they aren't really confined or limited to just one part of the magnet, but the whole magnet must have its own north and south poles. It's made up of many, many north and south poles that together form a collective north and south pole. How is this possible? Well, let's find out. If you continue this experiment and cut it into smaller and smaller areas, eventually you get it the magnets down to almost the atomic level. And here we are looking at so-called atomic level magnets. We call them magnetic domains. For example, consider this really, really small part of a magnet. It consists of a few magnetic domains, 6 in this diagram, and you see that in each domain is its own magnet. Now, the arrows indicate the magnetic direction of the attractions. So these magnets are made of atoms, and a magnetic domain is basically a group of atomic magnets that point in the same direction. But how is it possible? Well, how is it possible that you get all the atoms to align themselves in a certain direction in a way? That's quite a feat, if considering that uh, atoms are often in constant and really fast motion all the time. They're moving every direction, vibrating everywhere, so you wouldn't expect them to ever be aligned. In fact, this is true. You look at any unmagnetized bar, right? The domains will be pointing in various directions. So because they all point in various directions, they cancel each other out, and there is no net magnetism. Alright, but let's look at actually a magnet. When you bring this magnet near this unmagnetized bar, what happens? Well, each of the magnetic domains actually interact with the bar magnet, each one of them. Now you can just imagine, perhaps the ones that are closest to the bar magnet will be induced to become a magnet because they interact with the magnet, and then in term through induced magnetism, they cause the surrounding domains to also line up, and the surrounding domains have become uh, induced magnets through magnetic induction. And this process continues until the whole bar becomes magnetized and induced magnet in one direction. So what happens? Well, whereas in the center, right, the north poles of one domain will point to the south poles of nearby, and therefore causing the adjacent poles to cancel out. But however, at the ends, right, at the ends, the poles are actually free. They are not connected to any more domains, and therefore they become the net south and north poles of the magnet. In other words, while the whole magnet is actually consisting of many magnetic domains, they are joined together, all pointing in the same direction. However, the resultant magnetism, what you actually feel, is really the magnetism due to the poles, right? The atomic magnets at the both ends, which are actually free, which is why the magnetism is always strongest at the ends of the pole. Right. One last thing to highlight is that notice that at the ends, right, the arrows are not exactly straight, but they actually point a little bit outwards. Well, because here with a little bit of the space, right, and because there's no more the south pole next to the ends, or no more north poles next to the south ends to actually keep them in line, they will want to repel each other a little bit, so they start to fan out. So you can see towards the top right, the magnetic domain is pointing towards the top right, and towards the bottom right, the magnetic pole is pointing a little bit to the bottom right. Remember stroking? Here's a diagram, something that you should have seen a lot. Now, first of all, I need to highlight that you need to use a permanent magnet. That's for sure. You can't use an iron bar to stroke an iron bar. Secondly, you'll notice that the bar that's being magnetized is a steel bar. Steel is a hard magnetic material. When you say hard, it means that it doesn't lose its magnetism easily. This is in comparison to an iron bar, which can lose its magnetism pretty quickly. Alright, so this method, which we call the single touch method, where we need to lift the permanent magnet high enough at the end of every stroke, alright, to actually prevent whatever was induced from being cancelled when the magnet moves along the steel bar to the other end. In other words, you got to stroke it in one direction, then you can lift the bar high enough, and then you got to go back to the other side and start again. If not, you are ending up not magnetizing anything at all. While there's beyond the single touch methods, there's also the double or divided touch method, where the two unlike poles of two magnets are used to stroke the magnetic material simultaneously from the middle. So it starts from the middle going out. Alright, and so the magnet is able to form a stronger one when you use this method. But what if you, instead of using the unlike poles, you use the like poles, and then you use it to stroke the bar? Well, what will happen is that the two identical poles, they are opposite to the stroking poles, will be formed at the ends of the bar, and two poles identical to those of the stroking poles will be formed in the middle of the bar. In other words, you will have a really strange magnet where there are poles at the center and poles at the end. Well, that's something that you typically not want. Alright, let's look at the second method, which we had previously learned about, electrical method. Alright, and here in this case, again we use what we call conventional current, okay, connected to DC supply. Alright, so why is this a better method than the stroking method? Well, for once it's certainly quicker because you just need to turn on the current. Alright, and how would you make it stronger? Well, yes, you could increase the number of turns. You could certainly increase the current by strengthening the supply. And I guess you noticed the cardboard roll. Maybe you should replace that cardboard roll. But with what? Maybe an iron rod. Okay, so we will talk about this a little bit in a subsequent section. Well, after you have made the magnet using electrical method, how do you actually determine the direction of the magnet? We use the right hand rule. Right, so basically what you do is that you use your fingers of the right hand. Okay, you grip the rod according to where the current is going. So in this case, you see that on the side of the rod that's towards us, right, the current is actually flowing downwards. So you take your fingers and make sure that they also point downwards, okay, on the side that's closer to the us. Okay, and you see that where your thumb is pointing, that's where the north pole of the magnet is. Alright, and on the other direction it would be the south pole. Okay, and here's just a summary of what it says. Another way is actually imagine yourself looking into the coil. Right. So inside, let's say if you have to look into the coil on the left hand side, as so, you'll sort of see the current flowing like that, right, towards the more like a clockwise direction. And so in a clockwise direction, it fits the letter S pretty well. So that means that must be the south pole. If the current is instead in the anti-clockwise direction, then it fits the letter north pretty well, and so that must be a north pole pretty at this end. So whichever method you use, whether the right hand grip rule or you're looking into the coil, they both are good means to determine the direction or where the poles are. Next, do you remember we talked about demagnetization of magnets in primary school? Alright, so let's try and recall how we did it. Right, basically, now we were talking about hammering or dropping the magnet. The idea is to cause the magnetic domains, instead of being pointed in the same direction, now to point back in the random directions, so that any magnetism will be cancelled out. So this can be done in three ways. Number one, through heating, because when you heat, the atoms actually vibrate vigorously, right, and they no longer become aligned to each other. Alright, and in addition, right, and to finish off the stroke, you can actually put it off, lie the magnet in the east-west direction instead of in the north-south direction, so the domains do not automatically remain back in their north-south direction. Next, you actually hammer the magnet, again the same way, right, because when you hammer, alright, there's some movement of the domains, and this alters the alignment, and the magnet actually loses its magnetism. And again, it's recommended that you should do this in the east-west direction, so it will not automatically align back to the north side. And then there's the electrical method. This time we use an alternating current instead of a direct current, right? So the alternating current basically changes its direction in every second. It changes its direction about 50 times, right? So it causes the polarity of the magnet to change at the same rate. Right, so at the same time while it's changing, you actually slowly withdraw the magnet out of the solenoid or the coil, and so because of that, uh, eventually, right, the domains will be misaligned. It is important that when you do this, the solenoid should be aligned in the east-west direction, right, in order to minimize any effect of the natural tendency due to the Earth's magnetic field to lie back in the north-south direction.